Okay, students, I'm making a video that whatever could not complete in the classroom, I would like to finish it off. So this is lesson 9.1 continuation, PMA Maths 189, and this is about application of dot product. So the definition of dot product we've seen in my earlier videos also that if you have two vectors u bar and v bar, then it is defined as the magnitude of u bar, the vector u, the vector v, and the cosine of theta. So basically, all that means is if we have a vector, let's see, this is a vector, and there's another vector. So this is u bar, and this is a vector v bar. Then what is the meaning of dot product is it's the projection, or it is the scalar projection. That means I can drop a perpendicular from here and make this one. So this is if the angle is, so if this is the angle theta, if this is the angle theta, then this part, this is projection of scalar projection of this, which is u bar, because the magnitude is the hypotenuse times, or it is also along the v bar. The scalar projection along the v bar is cosine of theta, because by definition itself, cosine is adjacent over hypotenuse, and what is adjacent is this one, which is this scalar projection. We don't, let's imagine we don't know, I'll put it like a P, and the hypotenuse is the magnitude. So when you multiply both sides by this side, so this crosses, and this P, that is the projection, is that part. So this is, and what is the meaning of that? This vector is from magnitude from this to, so that's v bar. So this is vector v bar, the magnitude. Basically, the dot product is of u and v is nothing but it is the magnitude of u, magnitude of v, and whatever the angle is. This also will helps us if you have you can also write cosine of theta. If you want to find angle between two vectors, all you do is u bar dot v bar divided by, and then the magnitude, and you use the calculator and get the answer. Just to get an idea that this we can apply the dot product, how to find two vectors. Let's see if there is a one vector, find angle between the first vector, let's say, is 2 and 8, and the other vector is, let's say, 9 and 3. So if I want to find what is the angle between them, all you do is first figure out what is the magnitude of this, or I can make it more easier, this one. Let me take it as 6 and 8, and this I'll take it, because these are easy numbers, this I'll take it as 12 and 5, because if I think of, so if I think of 0, and this is like 12, and this is like 6 and 8, and this is 6 and 8 will be 8 somewhere here. So the one vector is 5, so this is 5, let's see, this is 5. So this is v bar, and the other vector is, this is u bar. So this is the u bar, 6, 8. Okay, and this one is 12, 5. So then we want to know how much is the angle, right? So what is this angle? So for that we need to know the magnitude. So the magnitude of this is, first one is the square root. So we can find out for this, the magnitude is the square root of 6 square plus 8 square, and which is 10. So this is 10. That's the u bar. This is the u bar. And the magnitude of the red color, that is v bar, is 12 square. The same thing we do, 12 square plus 5 square. and you work it out and you get 13. So this becomes your 13. So you want to find what is the angle theta. All you do is cosine theta from the definition. This is the definition. You can figure out the cosine. So cosine theta will be u dot v and the magnitude, right? So that's right. So the u magnitude is 10 times 6, 10 times the, sorry, so what is the dot product? So this dot product is, you multiply, this is like your A1, A2 and B1, B2. So the dot product also is, one more thing I did forget is, the dot product can be proved that, so this can be also proved that is nothing but it is a A1 plus A1 times B1 plus A2 times B2. So this is the magnitude, or it is just by the product of the, remember that I was saying the projection, scalar projection and the vector v, or in this case it is just drop a perpendicular. So that will be the, if I drop here, that's the u bar cosine theta, and then you multiply. It's same as multiplying 6 and 8, 12. So A1 to B1 is 6 times 12 is 74. So it will be, so 6, okay, that's 6 times 12, and then you multiply 8 times 5, and then that, and the bottom will be 10 and 12, because that's 10 times 12, and you get the answer cosine. Whatever that you get, maybe 74 plus 40 and 120, and you get 144. So it gets 114, sorry, so 114 and divide by 120. And then theta, you take the inverse. So theta is cosine inverse. With the calculator, you can figure out what is this answer. You're done. So that's how we can use the dot product to figure out the angle between the two vectors. But today's video, I wanted to show you how do we figure out. So the question is, how do we model forces? So we want to know how do we, what is the meaning of work done? So let's see what is this work done. In physics we have, what is the definition of work done? When a force of magnitude F moves an object through a distance d along a straight line, then the work is done. So the formula is nothing but W is force multiplied by displacement. So you know in science, work done is always force multiplied by displacement. So this is again another way to say force is in pounds. So we will consider force is in pounds, and the distance is how many feet. This is an example I posted here. How much work is done in lifting a 20-pound weight, and it is raised off the ground. Now I'm just giving a model to you. This is what it basically means. You just imagine this is not 20 pounds, and this is like is on the ground. And I want to lift it up. So when you lift it up, I have to put force. It means in order that it raises up, right? So when you raise it up, how much force you are putting is given as like how many pounds. So that force is like 20 pounds is given, and you are lifting it by 6 feet. So in this example, the work done is force. So the force is the weight, that's the force. So force times displacement. So the force here is 20 pounds, and the distance is when you're lifting it by 6 feet up. So and you get 120 we say pounds feet. So it is like lb and feet. So that's all it is about without vectors. See, it's just from pure science using the definition. But the question is, how do we apply this with the help of vectors? How does vectors help? Just imagine if there is a kind of a thing, there is a point here, you are lifting something from here. This is and you want to move something at that, and you're applying force in this direction, let's see. So the question is, what is the work done when you pull this? Let's see, when you're pulling this towards this way, anything here, you're just pulling. So that's what I'm trying to show in my in the other figure. Here it is. If you look at it. Okay, so what if, now the one that we showed was along the, it was either you lift, so that board, I lifted it and it went, so the movement of the object is in the direction of the force. So my force is in the not upward, so see the direction, and also the object is moving in the same direction. So that we can use directly, work done is force into displacement. Not only that, we can also pull this. I can just pull this along horizontally. So the movement of the object is on the same side where the force is being applied. But the question is what? What if I want to move this? If I'm putting a force on this, so if I put this force and I want to move this at some distance, I hope you can see what I'm trying to show. Yeah. So if I want to move that object from that position to another position. Okay. Now this one is horizontal, not necessarily always. It could be another way. So this is just an example. So when I put at some angle, I'm putting a force. See this one? There's an angle here, and when I have angle, this force is a vector. Now I'm putting a force. I'm pulling it, and as it pulls, you can see it goes in the, and it changes the position from here. When I can do, sorry, I can put more force, a little larger force, and it will go more distance also. So the same thing is shown here. If the object is right here, P, and force, and this force is not applied in the direction of, so the body, the object does not move along the force, but the object moves along the horizontal line here, along this vector. So the question is, how do we find this? So force is this is one vector where the force is going along, this is represented by OR, and the distance the object moves. So this is the object. This object moves right here. So when you pull this one like that, so this moves from P to Q. So you have a vector PQ. Okay. So by definition, so work done moving along this direction PQ. So this P to Q is the D. So this D stands for, let's see. So this D is like going. So again, I repeat, the object moves from P to Q because you're applying the force at some angle theta. So, so the work done moving along PQ is W. By definition, we know what is the work done. Work done is, we know it is force multiplied by displacement. So now in this case, the magnitude, I'm talking about the magnitude of force. Now force is F bar, that is F bar. So but this force, is it the same force? Now this force which you apply is not along the PQ. It is this force which you apply, it resolves into two forms. So one is horizontally. So this force is resolved this way. This is called horizontal force, this way until here. And remember, this magnitude in this direction, if this is the theta, we know that the scalar projection of this vector, green color, is this becomes this one, see, into cosine theta. And you know the reason is because cosine theta by definition is, what is cosine is? Adjacent over hypotenuse. Now here adjacent is this distance, whatever that, this part we don't know, I'll call it like a P, and divide by, not this P, this is uppercase, point P, this is the lower, okay, let's put some other, let me put maybe M. And then adjacent is this magnitude, which is the force, how much force you put, so that's the one. So then I multiply both sides by F bar, this I'm multiplying. And then this crosses out, and that m that you get, so the m is into cosine theta. There you go. So this answer, this is that m I'm talking about. So the force when you apply it at an angle gets resolved horizontally, so it can be resolved into two. One is this one, and the other one could be vertically also. And we are not interested in this the vertical, which is also v sine theta. So if you think of the perpendicular to this one, the one that we shown, that will be the same thing, but it will be force sine theta. We are not interested in that. We are interested in the one, the force that takes the object this along this one. So the resolved force of this when you pull is it makes the body move the object from P to Q. I hope that makes sense. Okay, again I repeat. So if this F was along like this way, then you will just use the same magnitude. But because it is going up, that means it is not the whole force. It is the force that gets divided into the force along horizontally and the force along vertically also. See? So this force is resolved into horizontal and vertical, but the horizontal force is the one that shifts the P to Q. And that is magnitude is this part. So what I'm going to do here is, instead of force, we write this part, F. This is the magnitude, how much force you are putting here, and then times cosine theta, and then the displacement. Now the displacement from P to Q, I'm going to use a vector. So D, now what is a vector? It's not just magnitude, it is also direction. So, and then in this is a vector, but you have to put magnitude, because that's the distance PQ. That's all it is. The distance PQ. This basically means P to R. So if I want, I can write here. Basically, this is P to R, and then times P to Q. Deixa mais chamar, tirar tudo. एक दावा पाने भी ना करें. दावे, दारा नहीं मार. Okay, so I hope this makes sense. Again, I repeat, I'm repeating this again and again because it's a little confusion. We know the definition that how much work done is when you put a force, how much force into displacement. But the point is the force is not along the direction of the object that is moving in the motion, but the force is other one. So that force, which is here, is always resolved into two. Means you have this force. It means like this one plus that one. So this vector is whatever you have, so this part. So there is another force. So this force is this plus that. So if I want you to write, you can write this is sine theta. So hope that happens. But this force is along this PQ, going from P to Q. That's why I'm writing this, and I'm repeating this again. So now the goal is, look at this. So now you have this. The work done is, I'm gonna just write this as F bar. Then I multiply. This is multiply. Okay, this is multiplication. I don't want to put the dot because this is like a. Okay, this is together. So this is not dot. Dot product getting confused. Actually, this is multiplication. This is together. Okay, so that. And this, instead of this, I'll use multiplication. I think we are getting confused. This means you are multiplying. Dot product is different now because, watch this. So this is multiply, and then into cosine theta. Okay, or instead of writing, we don't have to. It's just we write this cosine theta, and then then, or I will rearrange this. I think the better to rearrange. So this times the d bar magnitude and times cosine theta. Okay, and when you look at it, what you see here is this is same as writing, okay, the work done is, it is nothing but a vector f, this f dot the d vector d. Done. So basically what I'm trying to say is, if we have a force applied with some angle, then we can use the dot product by just knowing what is the vector. So we have to know what is this vector. So if you know what is this vector, let's say f1, let's call it as, I'll use a lowercase, maybe f1 and f2. So those are the component vectors for this one. And if you know this, if you know from what point to what point it is moving, then you just have to figure out this. So what you see here is, it doesn't have to be horizontally. What if it was something like this way, instead of P was here and the Q was here, and you're applying a force, and you're applying the red force, so this is the red force, and then you put so that angle will be theta, so that means this is moving, and this point they could give us with some coordinates, like you will be given some x1, y1 on the grid, and this point is given x2 and y2. So all you need to know is, what are the position vector here. So you need to know what is this vector. So this position vector basically means starting from the origin. So this vector will be x2, you subtract x2 minus x1 and y2 minus y1. That's all you do. And you get this vector. Once you get that vector, you'll be given the force. This will be given to forces, certain kind of a force is given by the vector. So if you see this, okay, that's a direct example. A force is given by the vector. So they already gave you the force vector is 2, 3. Now that's the position vector from the origin. It means 2 across and 3 up. So it is like 2 across and 3 up, something like this. See, this is 2 across. So it doesn't have to be from the origin. So what all you do is, you are given the force vector, but this force vector also can be written as 2i plus 3j. Okay. So this is the application. What I'm trying to say is, okay, let me first solve this problem. So first, how do we do this? How do we apply this formula? Is all you need to know is what is the vector f and what is the vector d. Now in this example, let's write solution. So how do we do this? So a force is given by the vector this. So that's the important part. You are given the vector f and moves the object from the point 1, 3 to the point 5, 9. Okay. So I'm gonna write that the point is moving from, this is like x1, y1, and this is your x2, y2. So we need to know from point P, and this is the point P to point Q. So that means we need to know, you are given the force vector, that is, so force vector is given to you as 2, 3, okay, and your distance PQ, the vector, that vector, you have to subtract this x2 minus x1. So the new vector will be, if you want, I can write a formula again, x2 minus x1 and y2 minus y1. So this will be 5 minus 1 and 9 minus 3. So there you go. So which is 4 and 6. So this is the vector PQ. So what do we do for is, we are using the dot product. That means all you do is force. So the work done is force dot the displacement, or this D. Basically what I'm talking about is the PQ, from P to Q, and the force is given to you right here. This is the one. This one you plug it in right here, which is 2, 3, and then the product. This one is 4, 6, and then this answer is nothing but 2 times. So all you do is your the dot product. So what is this dot product? This is again confusion. This is the A1, A2, and this is B1 and B2. So your dot product theorem, of which I'm going to show also why. To find the angle, I think, see if I have a u dot v, vector is u bar v bar into cosine theta, and then this is if you know the angle, we can find the dot product, but we can also, this is by definition, and we can also prove that, we can prove the theorem why the dot product is A1 B1 plus A2 B2. So dot product is also this one. So that's how we are using here right now. So I'm going to just multiply this 2 times 4, so the new vector, so not new vector, it is the scalar value. So it is 2, this 2 times 4. So the formula is A1 B1 plus A2 B2, which is 2 times 4 and plus 3 times 6, and you get 8 plus 18 equals 26. And that's all it is. So this is the force, this is the work done. We don't know, the units are not given, but it could be like pounds, feet pound in the earlier example. Hope this helps. And then if you want to really see this, I'll just try to make an effort here. So let's see the point that was given to us was 1 and 3. So the first point was 1, and this was 1, 2, 3. So they gave you a point here, P, and then the Q was 9. What was the point? I forgot. 1 and 3, and then 9 and. So it was 1 and 3. Oh, let me check on. I forgot. Okay, let me get it from here only. X2, Y2, so Y1. So X1, Y1. So 1 and 3, correct? And then 5 and 9. So 5 and 9. 1, 2, 3, 4 and 5. 1, 2, 3, 4, 5, 6, 7, 8, and 9. So this point is like this. This is Q. Now this object is moved like this. See? That's the vector. And the another vector is given to F was 2, 3. So what they gave is there is a 2, if this is 2, and somewhere I'm making a mistake. This is 1, 2, 3, correct. So this is 2, 3, is 1, 2, and 3. So somewhere here. Somewhere 1, 2, maybe here. So this vector was given to us. This is the vector. This is the vector F bar, right? Now they gave us the this is position vector. Now why I call this as position vector is this was 2 and that this is like 2, 3 because this is given to us. See this part 2, 3. So this point is 2, 3, but the vector is position vector is 2, 3, or it is also 2i plus 4j. It's because this is the unit vector I along this one, and this is the unit vector along the y-axis. So I have 2 of this I, so this is another I, and then you have 3 I, like I say, 1, 2, and 3i. So that's so we don't have to show all this, just to make sense that okay, it is this vector. Now I can always shift this vector. See, I can have the same vector somewhere, something like this also. This is 2 and this is 3. See, so it's like 2 run, 3 up. I can have another one, 2, and this one also. See. But then I want at that position, so because the force is applied here, so I need to go from here. So this is the place I'll have to go. Okay, 1, something like this, 1, 2, and then I go 1, 2, and something like this. So it's like the same thing, but applied like this, see? So this is where the force is applied. This is the F bar. This also is F bar. Huh. So am I making sense? Yeah. So they gave you the point. This dot is pulled by force that with some angle, whatever that angle, we didn't say. There's too much of too little, and then when you pull that force, that takes it to Q. So yeah, the Q 5,9. This was the point. The point is 5,9, but the vector is 5,9. So be careful with. So the vector is 5,9, not the point, just a 5,9. So just one minute. 9 x2 y2 is 5,9. Yeah. So this is 5,9, but this is 5,9. I'm making a mistake. Wow. So this is 5,9, correct? But the vector, position vector that from P to Q, d bar. So the d bar that we have here is, the d bar is PQ. So this is 4, 6. So this is 4, 6, this vector, that is d bar. So this is the black color force, is that. So the geometrical interpretation is also important. Of course, they didn't ask this question, but I'm still thought of showing, okay, we do the work, we finished, done. But how do you understand geometrically? You can see that there was a vector from this P to Q, and there is a force applied by 2, 3, and the 2, 3 is basically component as 2 and 3, and I try to apply it at this point, so I have to go that way, and there is an angle form, and that's how, this is the one which moves that from P to Q. Okay, so that completes this. In the next class, I'm going to also prove why two vectors u bar and v bar y. So this is the next video, and after that also we'll see very soon what is the cross product of this. What is u cross v then? Okay, hope this helps. Thank you for watching. Make sure you go through this. I know I speak a lot, and oh my God, that's too much of work. And then, but the point is, can we understand this in real life? How this forces get. Remember, when a force is applied in a certain angle, it will always resolve into two parts. It can be along this. If you do along this, then the other one is perpendicular. Always, no matter where. So if one more thing I want to show is, so in other words, there is when you apply this force, the same thing when you apply the force there, if this is the force applied, then there will be angle form, and one is along this, whatever this force is over there, it is F bar, right? So when you drop, this is 90, this is that F bar cosine of theta, whatever the angle theta. But then there is also vertical. So the red one force resolves one along this, whatever that, this part, and the other one goes perpendicular like this, until here, sorry, this. So this one and this way. So you kind of form a rectangle out of this. So we will see also the other later classes is where how if there is a car like this. So if this is a car, oh my God, doesn't look on the road. Now this car gives stress on this ground. See, there's a weight of this, like that is weight, we can see W, and then we will see that if this car is kept, so this one there's only is downward weight of the car on the road, but if the road is this way and the car is like this way, then what you see is, so see this part, if this is the car, then the car can roll down. So they ask you, suppose the weight of the car is less than 2,000 pounds, and how much weight should I apply so that it doesn't roll down? So this car, the actual weight is W. It goes because of the gravity W. That's what it is. But now, and then this also puts stress on the road this way. See? So this is like, and there is one force. So one force. This W, whatever the weight gets divided into two, one along this one and one along this one. You can draw draw a rectangle like this. So these are the problems that we will see in the next class. So hope that helps. Thank you for watching.